To size a 550 kVA three-phase generator with a line-to-line voltage of 400 volts and a line-to-neutral voltage of 230 volts at 50 Hz, consider these steps. Firstly, convert KVA to kilowatts. KVA, which stands for apparent power, equals kilowatts, which is real power, plus kVAR, which is reactive power. In many practical scenarios, the reactive power is quite small compared to the real power. Therefore, we can make the assumption that KVA is approximately equal to kilowatts. In this case, the real power, or kilowatt rating of the generator is approximately 550 kVA, which means approximately 550 kilowatts. Secondly, calculate the amperage per phase. For a three-phase system, the current or amperage per phase can be calculated using a formula. The formula is as follows: the current in amps per phase equals the kilowatts divided by the square root of 3 times the line-to-line voltage, taking into consideration the 50 Hz frequency. Using this formula, current per phase equals kilowatts divided by the quantity, square root of 3 times voltage line to line. Plugging in the values, we get I phase, which is the current per phase, equals 550 kilowatts divided by the quantity, the square root of 3 times 400 volts, which approximately equals 633 amps. Thirdly, determine whether to divide by 3. Whether or not you divide the calculated amperage per phase by 3 depends significantly on the load type connected to the generator. Consider the scenario of a balanced load. If the load is balanced, this means that the current drawn on each phase is equal, then you do not need to divide the calculated amperage by 3. The 633 amps represents the current in each phase. Now, consider the scenario of an unbalanced load. If the load is unbalanced, meaning that the current drawn on each phase is different, then you may need to consider the current per leg differently. If a significantly unbalanced load is possible, further investigation may be needed. In conclusion, based on the information provided, it's important to determine if the load is balanced or unbalanced. If the load is balanced, the generator is rated at 550 kVA, and the amperage per phase is approximately 633 amps. If the load is unbalanced, further investigation into the load characteristics will be necessary to determine the current per leg accurately. Keep in mind that the formula used to calculate amperage assumes a purely resistive load and doesn't account for power factor. In real-world applications, the power factor is rarely 1, and this affects the amperage calculation. The formula that includes power factor is as follows: current equals kilowatts divided by the quantity, square root of 3 times volts line to line times power factor. The power factor is the ratio of real power, kilowatts, to apparent power, kVA, and is a decimal number between 0 and 1. If the power factor is less than 1, the current will be higher. For example, if the power factor is 0.8, the current per phase would be 550 kilowatts divided by the quantity, the square root of 3 times 400 volts times 0.8, which is approximately 791.25 amps. The generator's specifications usually include a power factor. Always refer to the generator's datasheet for this information to perform accurate calculations. Generator sizing also involves considering several other factors, including altitude, ambient temperature, and the type of load being supplied. High altitudes can reduce the generator's output, as the air is less dense, resulting in less efficient combustion. High ambient temperatures can also affect the generator's performance, as the engine may overheat if it is not properly cooled. The type of load being supplied can also affect the generator's sizing. For example, motors require a higher starting current than resistive loads, so the generator must be sized to accommodate this inrush current. When sizing a generator, it's essential to consider the total load that the generator will be supplying. This includes all of the lights, appliances, and equipment that will be connected to the generator. It's also important to consider any future loads that may be added. To calculate the total load, you can add up the power consumption of all of the individual loads. Power consumption is typically measured in watts or kilowatts. You can find the power consumption of most appliances and equipment on the product label or in the user manual. Once you have calculated the total load, you can use this information to select a generator that is large enough to supply the load. It's always better to oversize the generator slightly to ensure that it can handle any unexpected loads. Regular maintenance is crucial to ensure the generator operates efficiently and reliably. This includes regular oil changes, filter replacements, and spark plug replacements. It is also important to check the generator's voltage and frequency regularly to ensure that they are within the specified limits. Furthermore, ensure that the generator is properly ventilated to prevent overheating. It is also important to have the generator serviced by a qualified technician on a regular basis. A qualified technician can inspect the generator for any signs of wear or damage and make any necessary repairs. It is recommended to keep a detailed record of all maintenance performed on the generator. This record should include the date of the maintenance, the type of maintenance performed, and the name of the technician who performed the maintenance. This record can be helpful in troubleshooting any problems that may arise with the generator in the future. Remember to consult with a qualified electrician or generator specialist for accurate sizing and installation. They can assess your specific needs and ensure the generator is properly installed and connected to your electrical system. They can also guide you on best practices for generator operation and maintenance.